Hi, Mr. Bricker. These are my definite and indefinite problems for the integrals. So first we need to find the interval, or the interval. So it'll be 2, 5. This one doesn't have one since it's an indefinite integral. So first we need to find the antiderivative of this. So it will be negative 1/3 x cubed minus 3 over 2 x squared plus 5x plus c, because we don't actually know, because we have to take these numbers to subtract it by. And then we know the differentiation, so we're gonna have to do f of 5 minus f of 2 to find the c. Therefore, when you plug all these numbers in, it'll be negative 1/3 5 cubed minus 3 over 2 x squared, or 5, and then 5 times 5 minus 1/3 2 cubed plus 3 over 2 squared plus 10. From this we go and find these numbers. So this will be 125 over 3 negative, and then this will be 25 times 3, so 75 over 2, and plus 25, and minus, I'll be 8 over 3, plus 12 over 2, plus 10. And then we combine these all together. And this will be distributed equally onto that, so we need to make this accordingly. So this will be minus and this will be minus. So then we'll get negative 125 over 3 minus 8 over 3, and then we'll add plus negative 75 over 2 minus 12 over 2, and then minus 10, so it'll be plus 15. And then we'll simplify this down to negative 133 over 3 plus, then over here we got 87 over 2 negative plus 15. And I'll simplify this on my calculator, but this will be plugged back into that to get that number. So yeah, and then for this one, it's pretty simple. You just take the antiderivative of this. So this will be 2/3, 2 over 3 x to the third minus 7 over 2 x squared plus 2x plus c from whatever this derivative is. And that is it. Here's my next problem. It is a problem about the antiderivative and going back down and up from the derivatives of acceleration, velocity, and position. We already know that we have the acceleration time, the velocity of time, the position of time. And we know that we can go from this, like this, with the derivative, but using the antiderivative, like we are in this problem, we can go from acceleration back to position versus just derivative going the other way. So this is how we're going to find how long it takes before the car stops and how many feet we travel. So for this, we know that our car is decelerating, so our acceleration will be at a rate decelerating. It will be at negative 15 feet per second. And we know that when v of t equals 0, we know that that's when the time, when it's 0, that's when we know it stopped and how long it takes to stop. So from this, we can figure out the antiderivative and then plug that in. So we take the antiderivative of negative 15 and from this we get v of t equals negative 15 t and then plus c but we know that it was traveling at a rate of that before it gets to that, right? So we can plug, instead, we know this constant because it was traveling at a rate of 88. So then our v of t will be like this. And then from there we can solve for 0. So we can get 0 equals negative 15t plus 88. And then this works out to be 15t equals 88. T equals 88 over 15, or 5.87 seconds. And that's how long it will take for the car to stop. It will take 5.87 seconds. And how many feet were traveled during that span? We know that the car is traveling at a rate of 88. And so we need to take this equation that we found by taking the antiderivative. So this is the double prime, so this will become the prime. And then we can antiderivative this in order to get the position, and then we can plug in the amount of seconds traveled in order to get that position. So we're going to take the v prime of t, and we're going to make that equal to negative 15t plus 88. From this, we can take the antiderivative, and we take the antiderivative, and then we get 7.5 t squared, negative, and then plus 88t, which equals, and then from this equation, 8 to 15, because that's how far we're going, 15, and then we use f of b minus f of a to solve for that position in time, which will be negative 7.5 88 over 15 squared minus 88 times 88 over 15. And then we're just plugging the 88 over 15 to 0 in to find how far we traveled. And that comes out to be, the position comes out to be around 258.137 feet. So that's how far it travels to answer during that time period of 5.89 seconds, or 88 over 15. And then we're doing how far is the area bounded. So this will be an area under the curve, and we'll figure it out just using the antiderivative. So first, we need to set up an integral. We know that this is going to be on top because it's going to be like that, and then it's going to be an x like this, right? So we're going to know that we're trying to find this area on a curve, and then rotate it around, you know? So first we're going to set up the thing with the integral being from -1 to -3. That'll be -1 to -3. So it'll be 2x minus 4 minus x squared plus 6x minus 1. Then it'll go from this to this one over 3, negative x squared minus 4x minus 3. So that's just putting these two together, dx. And then we solve using the antiderivative. So this will come out to be 1/3 x cubed minus 2x squared minus 3x from -1 to -3, and that's where we're going to find the c value. So that'll be f of b minus f of a, and then and then we use this equation, plug in those numbers, -1/3, -1 cubed minus 2, -1 squared minus 3, -1 minus 1/3, -3 cubed, minus, oh, since this is minus, this will distribute. So these will be plus, I'm pretty sure. Yes, that'll be. So it'll be 2 minus 3 squared plus 3 over negative 3. And from this, we'll find out that C value. So this will turn out to be 1/3 minus 2 plus 3 minus 9 plus 18 minus 27. 27. And then this will add up to be 4/3. So that will go into that number, back into that equation. From that equation, we can solve, or that is just going to be the equation to solve for the area bounded under the curve. Okay, this is the volume of a solid region rotated around it, around the x-axis. So this will be, basically, you have a curve, and let's say, I know this is not the actual depiction of these numbers, but let's say you have like that, right? And that'll be rotated 360 degrees around the x-axis, and that is the volume that you're looking for. So therefore, we know that it's going to be r squared, pi r squared, because it's going to be in a full 360 degrees. And you know this, and then you're going to solve by taking the larger function and subtracting it by the smaller one. So then we're going to put this one on top, put that one there, and then we're going to square them because it's pi r squared. And it's from an integral of 3 to 0, so we know that. And from this, we're going to simplify them out, and then we're going to simplify them together, and then we're going to take the antiderivative from 3 to 0. So then we're going to use the f of b minus f of a to solve for the total volume of 156 pi. And we know that that's going to be the volume since we're taking the outer, and there's a smaller circle in here. We're taking the outer and we're finding that area using this formula, or using the antiderivative and the difference separating, or the difference of calculate theorem. And lastly, we have a Riemann sum problem. From this one, I used the left Riemann sum. So basically, we go up from the graph to the line, and then across, and from the graph, or from the x-axis to the graph, and then across, from the x-axis to the graph, across, from the x-axis to the graph, and across, etc., etc., etc. And from this left estimating problem, you see that there's overlay from the graph on both of these sides. If you were to flip them onto the other side, they would account for the missing area in here, so giving you an accurate tally and square footage of the actual area. And from this, you add up A, B, C, D, E in order to find the total area under the curve. So we know that this is 2, we know that that is 4.5, we know that that is 5, we know that that is 4.75, and that is 3.5, just because each of these is 1, and their certain y value is according to that, giving them that total area. From that, we get 12.5 as our total area under the curve of this problem. And that is it for integrals. Thank you, Mr. Bricker.